This is lecture number 19 on Kalimantan Theorem, minimal polynomial, and analytic polynomial. So this is a new topic. Basically, it's a slightly different topic than that vector space and other thing. It's closely related with matrix, but this is very important. That Kalimantan theorem is very useful for other aspects to find inverse and other things. So what is polynomial of an operator? So we know what is operator, linear operator. So this is a V is a vector space, V is a vector space to another vector space V. So V to V, say linear operator is V to V. T is a linear operator from V to V, a linear transformation from V to V, which is called linear operator. Linear operator means it is both are V, domain and codomain. Now, so what is a polynomial of the operator? So what is sum and product? So two, we know what is sum. So sum is just T plus S, just T plus S, V equal to TS, TV plus SB. Now what is product? So say T square or ST. What is it? By definition, T square is not just T square of V is TV whole square. Is actually T square of V is TV T of TV. So it is composition. So product here composition. So it's not just T square, TV whole square. Because if it is TV whole square, then it is not a linear operator, non-linear. So if we define the T square like T square V as TV whole square, then it is not a linear. So say the identity of operators, TV equal to V. Now T square, if you define T square V as a TV whole square, that is V square, V goes to V square. That is actually undefined basically. How do you define in general vector space V into V? So T square V means it is just T of TV. So now we can talk about any polynomial like say 3t cube minus 2vt square plus say 3t plus, no, you can't write that as a 5. You have to write 5 identity transformation, operates on V, then it will be some T 3 of T V and like that. So this is a polynomial of the operator. But what is a polynomial matrix? Again, same thing. So for say polynomial matrix, we know what is say 3 a cube minus that we know 3 cube minus 2a square plus 3a plus 5i. Now we know if V is a finite dimensional vector space and we have a fixed ordered basis, then there is nothing difference between this linear operator and n cross n. If V is an n dimensional vector space, then every n cross n matrix there is a corresponding linear operator, and for every linear operator there is corresponding n cross n matrix. And if you fix this the ordered basis, the order basis for the same for this both V, then this linear operator is actually uniquely represents some matrix, and matrix has unique representation of the transformation. So matrix and transformation linear operator and n cross n square matrix of that square matrix of order n and the vector space with n dimensional vectors, finite dimension n. Then this linear operator and this matrix has actually no difference. There is a bijection. It's a natural bijection on that one-to-one corresponding between. So we can say whatever is linear operator or is it matrix. We can say same thing. All the theorems are same for linear operator as well as the matrix, just for finite dimensional vector space and for a fixed standard basis. For infinite dimensional vector space, there is nothing. Matrices there is no corresponding of matrix of a linear operator. Linear operator is always there for a infinite dimensional vector space also, but there is no corresponding matrix. Okay, so we are just talk with only finite dimensional vector space. So in that case, that matrix and this linear operator are same. So polynomial operator and polynomial matrix actually the same. So why this same? Just you have to look close that is t, if A is correspond to T, is A square correspond to T square? Yes. If A is correspond to T, then A square correspond to T square, because we know that if T squared is this, so for a corresponding basis, say T from V to V, and correspond some base standard basis say VB, the corresponding matrix is A. So A is just the corresponding matrix of this transformation with respect to standard basis. Then we know that A square is the transformation of T square, corresponding matrix of the T square with respect to the same standard basis. And not only for A square, actually, if A is the correspond T and B correspond another matrix correspond S, then AB correspond TS. So order is important. AB correspond TS. So AB base. So if A correspond to T and B correspond to the some S, is T and S a linear operator, and A or B two matrix, and the same order basis for both, then the TS, which is S acting first, then T, then it is correspond to the AB, B acting first, because we are just taking the V in the right hand side. So TV as like it's AV. TV in that the coordinate of TV in the order basis, standard order basis beta. So since it is right side, so this AB equal to TS. Sorry, AB is a corresponding matrix of TS. So we can talking about whether it is operator or matrix, it is same for a fixed order basis. Now, what is matrix equation? And matrix as a solution of an equation. So matrix equation means, so we can write like that, say some variable like that, say x 1 minus x, so 2x, say x square, then one matrix like that. So now this is a matrix equation, like a there is some variable in matrix. So you can think this like a two different way. One is there is a matrix, and in matrix, this matrix has a entry with integer variable, what we have to solve. On the other hand, you can think like that, so some x into some matrix 1 2 0 5, say, then so first say 1 0 minus 1 3 plus this, then say x squared into some another matrix, say 2 0 1 0, and you can write this as like that. So it is just x 2x squared plus x plus 1. So this you can think in the two different way. One is an equation is like a polynomial, but the polynomial coefficient are from the matrix, number one, and you can think that that is a matrix but the entries are polynomial. Two different things. And the next thing is the matrix as a solution of equation. So what is this? So matrix as a solution of equation means, so say there is the equation, say x cube plus 3x plus 5 equal to 0. So now some matrix is a solution of this equation. What is the meaning of that? The meaning is this: a matrix A, it's obviously a square matrix, otherwise a cube is not defined. A square matrix is a solution of this equation, means A satisfies this equation. That means a cube plus 3a plus not 5, it is 5i, i3, say in the same order of A. So there are three different things. So one is a matrix with some polynomial as entries. Another is a polynomial with matrix as a coefficient. These two are same thing. And other is a matrix which satisfies some polynomial equation, satisfies some polynomial, but zero of the some polynomial. That is actually is a matrix equation. There is no x here now. So A satisfies this. So you have to very clearly know what is this, what is this matrix as an equation and matrix as a solution of the equation. Carefully have to notice that. Now, so annihilating polynomial. What is annihilating polynomial? So we talk about the annihilating polynomial of a matrix, and then it is actually for the linear transformation also for a standard basis, fixed standard basis. what is annihilating polynomial of a matrix or linear transformation? So again, see, if I take fx is a polynomial, some polynomial, then f of a, and what is f of a? We just write what is f of a. Say for example, fx equal to say x cube minus 3x plus 5, then f of a cube minus 3a plus 5. And similarly, for if t is a linear transformation or linear operator from V to V, then f of t is just defined as t cube minus 3t plus 5. I is the not the identity matrix, I is the identity linear operator on V. Now again, if t correspond a correspond to the matrix linear transformation T, then this f of a correspond to f of t. So we can think these two are basically same. Anything you can just do with matrix, or you can do with linear transformation. So now a polynomial f is called annihilating polynomial of some matrix or of a linear transformation T if this f of a is a null matrix or f of t is a null linear operator. Everything goes to zero operator. So if f of a equal to 0, 0 means null matrix of the same order, then this f is called annihilating polynomial of a. This f is called the annihilating polynomial of a. Now, if null matrix, if you take the null matrix, the any polynomial annihilating that null matrix for any f. No, not for any f. Sorry, this the constant term must be 0. Yes, so constant. If constant term is 0, then any polynomial whose constant term is 0, that annihilates the null polynomial. Because if you take fx as a say 5, just 5, then f of 0 is 5i. Is not null matrix. F of null matrix is just 5. So not every polynomial annihilate that null matrix. The constant non-zero constant polynomial not annihilate that. So actually non-zero constant polynomial does not annihilate anything in any matrix. Now T be a linear operator on finite dimensional vector space, then there is a polynomial which annihilate T. Similarly, if A is the similar corresponding matrix thing is this: if A is n cross n matrix, then there is a polynomial which annihilates C. Now this seems like to be Kalimantan theorem, but we can easily prove that without Kalimantan theorem also. That is very easy. So if say T is a or you can take as A. Now okay, you choose A. So take A matrix, then take A square, then A cube. Now up to go with start from I. So a to the power n square. Now A forms actually n square dimensional vector space. Now all matrix of n cross n matrix forms n square, a vector space of n dimension n square. Now since there are n square plus 1 many vector in dimension n square, so this cannot be independent. This set is dependent. That means there is some non-zero constant such that a0 a1 dot dot or c0 c1 such that this c0 I plus c1 a plus dot 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 cn square an square, this is 0 for where c0 c1 cn square is not all 0, some may be 0, and that correspond you got this that polynomial, the polynomial of x cn square x n square like that c1 x plus c. So this polynomial annihilates actually that A. So we can easily prove that there is a polynomial which annihilates as matrix, or same for linear transformation also, linear operator also. No need of Kalimantan theorem. But the question is, we got a big degree polynomial, say n square degree. But actually we can do with less degree with n degree polynomial. That is a Kalimantan theorem. And obviously we can do with a much more less degree polynomial. Like say a null matrix of order 4. No need of going to the order degree 4. Just x, polynomial x annihilate that. So there is a maybe much lower degree polynomial than n. Now that is a thing is called minimal polynomial. So you collect all this polynomial which annihilate A or T. Now this is a non-empty set because we have a polynomial. We know there is a polynomial of at least degree n square. If you go to that up to n square degree, there is a polynomial which annihilate that A. Now, so this set is non-empty. So take the minimum degree, and that minimum degree. But again, for minimum degree, there is a several polynomials. So if x cube plus x plus 1 annihilate that, then 2x cube plus 2x plus 2 also annihilate this. So you have to take the monic polynomial for a uniqueness. So that means the minimal polynomial is a polynomial, minimal polynomial of a matrix or minimal polynomial of a linear operator is a polynomial which annihilate that matrix and which is a less among the all polynomial which annihilate that matrix, and this is a monic polynomial. So three conditions. First of all, f must annihilate that, and then if any g annihilate a, then f divides g. So f is a factor of g, and f is monic. Now in that case, this f is unique. By the way, if whether f is exists or not, such a minimal polynomial exists. Yes, it is exists because this set, the set of all such polynomial which annihilate that a, that is non-empty. So since it's non-empty, we have a polynomial among them which is a least degree. Take that thing and then take the monic of that monic polynomial. Now there is one question. The question is this: so if it is a least degree and monic, is this a factor of all annihilating polynomial? That's the question. Is this satisfy the condition? We can take that as a just okay. In the definition, I think no. In the definition, the 2 is not there. Sorry, in the definition is 2 is not there. The definition is says that this is less among the other polynomials. Sorry, not that. Then degree of f is less than or equal to degree of g. So this is a definition, and that is a theorem. It is something like that GCD, similar type of GCD. So what is GCD? So GCD of AB is G is some condition is there. So that first condition is if any other common, first of all, G is a common factor, and then if there is any other common factor, then G is less than or equal to that factor. There is the one thing, and other thing is okay. There is the other definition is this: if any number which is a common factor of both A and B, then G divides that. So these two are equivalent. We know these two are equivalent, but obviously this is a stronger statement. If I say if G is GCD such that if any common factor of A and B, then G divides that thing, then this is a more stronger thing, more information is there. But again, this is two are equivalent. Same thing is here. So there we took less than and equivalently divisor. Here also same thing. We take the less degree, the least degree, or equivalently we can take f is such a polynomial which divides all the polynomials which annihilates that A. So this is a theorem. So monic polynomial, if you just take that as a definition, this as a definition, not that theorem, the degree less than f degree of f less than or equal to degree of g, then the existence is trivial. So there is a set where it is non-empty, and there must be a polynomial which has the least degree, and there is a polynomial among them is a monic. So you just divide by that leading coefficient. Now, is this unique? Yes, it is unique. Why it is unique? Because okay, take there are two polynomial which is minimal. Now, since there are two polynomial, both are least degree, cannot be both. So degree is same, and once degree is same and they are both are monic. Now if the two such polynomial exist, then what happens? Then the difference is also annihilate that A. Now the difference is now the lesser degree. So if F is a minimal polynomial, G is also minimal polynomial. So F annihilates A, G annihilates A. F and G are both same degree because both are the minimum degree, least degree, and both are monic. So the difference is again annihilate that A, but we assume that in the definition we this no polynomial lesser than that degree of A for G can annihilate F. So this is unique. Now minimal polynomial divides every annihilating polynomial. This is theory. Why this minimal polynomial divides every annihilating polynomial? Okay, the idea is like same in division algorithm. So take F as a minimal polynomial, minimal, and G say any polynomial which annihilate, G annihilate minimal of A and annihilate A. Now what is this? So that means F of A is 0, G of A is 0, and degree of F less than or equal to G, and F is monic. Now we just divide that G polynomial with F because degree is less. Now we have a remainder. So we have to prove that that remainder is 0. That remainder polynomial is a 0 polynomial. Done. That we have to show. Now if it's a quotient polynomial is a QX. Now Gx equal to actually Fx into Qx plus Rx. Now G annihilate that, so that is a equation that if you put A here, so if you A satisfies this, so what happens? So because it is identity, remember this is identity, so for a this also true, so it is identity. Now what happens? So we got this is 0, this is 0, so RA is 0. That means R is also a annihilating polynomial, but less degree of R is less than F, so there is a contradiction. So that means every minimal the polynomial minimal polynomial divides every annihilating polynomial. So it is just basic division algorithm. Oh, sorry, this is then this T must be there. So let A be n cross n matrix, then the characteristics and the minimal polynomials of A have the same root except for the multiplicity. This is the most important result. We'll see in the next slide that Kalimantan theorem says that characteristics polynomial is an annihilating polynomial. The characteristics polynomial of A is an annihilating polynomial of A. Now, therefore, if you assume that theorem, so Kalimantan theorem, that characteristics polynomial is an annihilating polynomial, and minimal polynomial divides that. That means minimal polynomial is a factor of the characteristics polynomial. But you have to show the other way. That means every root of minimal polynomial are the root of the characteristic equation or characteristic polynomial. But you have to show the other way that every root of the characteristic root basically is a root of the minimal polynomial also, except for the multiplicity. Maybe characteristic roots are the polynomial may be x cube or x minus 1 whole square, and minimal polynomial is just x into x minus 1. So you have to use that Kalimantan theorem to show the one side, and to show the other side. How do you show that other side? So if alpha is a characteristic root, that G is the characteristic polynomial, say, then what happens? How do you show this? So okay, I'm just leaving this one first. We'll go to the next thing. we'll just leave it for this one. The minimal polynomial of a diagonal matrix. What is the minimal polynomial of the diagonal matrix? That is easy. For a diagonal matrix, the minimal polynomial is easy. What is the minimal polynomial for the diagonal matrix? So this. So this is just product of x minus di, right? I equal to 1 to n, is it? But if di is not distinct, then what happens? So you have to take the distinct entries, right? So it's not that. It's not. This is not. This is a characteristic polynomial. So product of I equal to 1 to n x minus di is a characteristic polynomial, but this is not the minimal. You can show that the minimal polynomial is like that. So this is all the distinct thing. Say what is say? Should I say di? Should not be say di. It is a di dash, where di dash, the set di dash I equal to 1 to k are the distinct diagonal element. So that means the minimal polynomial is just the product of some distinct linear factor. But it may not be true that every minimal polynomial is always the every root minimal polynomial as every root of the minimal polynomial is just simple. It's just multiplicity 1. May not be so happening. There is a polynomial, minimal polynomial like x square. There is a polynomial. So there is a, what is the polynomial? Say 0, 1, 0, 0, right? Yes. In that case, it is a, then s square equal to 0, null matrix. So here the minimal polynomial is x square, not x. And x square is the characteristic polynomial also. So that does not mean that the minimal polynomial has all the roots as multiplicity 1. But for the diagonal matrix, it is true. The minimal polynomial for diagonal matrix is the product of the distinct x minus di distinct. So you can just easily check that why this is true. That take a simple example like say 1, 1, 2, 0, 0, 0, 0. What you have to show? You have to show that x minus 2i into x, sorry, a minus 2i to a minus I is a null matrix. That you have to show. Now this is true because once we get x minus 2i, a minus 2i, that will give actually 0, 0, 0, 0, 0, 0, 0, 0. Sorry, for it is a minus I, 0, 0, 1. And this is just minus 1, 0, 0, 0, minus 1, 0, 0, 0. It's like a block thing. So since it's a block part, this will give a null matrix. And this is true not only for this example, this is actually true for any diagonal matrix where some diagonal entries are repeated. But whatever the repeated, if it is repeated, that block will be that 0. If we take the x minus a minus di d1i, that this matrix is actually diagonal matrix with some diagonal elements are 0, where the which diagonal element is 0, where the d1 is there. That is like a block thing. Block is a block, there is a null matrix, other is there is a block for non-null. Is a diagonal, and this is true for everything and every factors. And the idea is that every factor, for every factor there is no overlapping, that 0 blockings and no overlap. So there's a zero like this type of things, the matrix, these are zero block. Off diagonals are zero, these are non-zero. Again, then this part is non-zero, say this block is zero, then again non-zero, some non-zero. So again, there's no overlapping this with this non-zero thing. So that's why this you can easily check that this will be a null matrix. So this is true. Now similar matrix have the same minimal polynomial. That is easy. That is very easy. Why this similar? So similar means that is P and Q are similar if, or A or B are similar if P inverse A P is equal to B. Then this is called A and B is called similar. Now minimal polynomial is same for the both. Why? So this is easy because what is this? So f of B, what is f of B? So f of B is just you can easily check that is P inverse f of A P, because B square is actually P inverse A square P. B cube is actually P inverse A cube P. So f of B is P inverse f A P. So if f A annihilate f A is null, then f B is also null. And if f B is null, then f A is also null. And for the same thing, we can say for the monic, if it's f is monic, then oh, sorry, what is this? No, f is the minimum thing. Why this? Okay, no. First we take f as a minimal polynomial of B. Okay, take f as a minimal polynomial of A. Then what happened? Then f A is 0, and then f B is 0. So f is an analytic polynomial of B. Similarly, if you take the polynomial which is a minimal polynomial of A, actually all the polynomial which annihilate A, that polynomial also annihilate B, right? No need of minimality. So let f is an annihilating polynomial of B, then f is an annihilating polynomial of A, and if f is an annihilating polynomial of A, then f is an annihilating polynomial of B. That means the set of annihilating polynomial of A and B both the same. That means the minimal polynomial is also same because the set is same. And the Kalimantan theorem, I will not prove this. Any standard textbook you can get this proof. The Kalimantan theorem. What is Kalimantan theorem? It is just the characteristic polynomial of A satisfied that A itself. So that means the characteristic polynomial of A is an annihilating polynomial of A, and this actually used for finding inverse of a non-singular matrix. And not only the Kalimantan theorem is used. It's actually if you can find the minimal polynomial of A, and once you can find the minimal polynomial is a least degree, say it is a say a cube minus 3a plus 5i 0, then you can easily find what is the inverse, because it is just a square minus 3i equal to 5 minus 5i, and you can find what is the inverse of that. So inverse of this is just 1 by 1 minus 5 a square minus 3i. So no need of going to the analytic that characteristic equation. If you can find the minimal polynomial, that will help much. Otherwise, if you can't find the minimal polynomial, you have to go with that Kalimantan theorem to find the analytic polynomial. Once you got any analytic polynomial, you can easily find the inverse of that. And we know to finding inverse in that adjoint technique or any other technique is much computing labor is much computing power is needed. But for product finding a square there is a lesser number of computation. So in computation purpose, a perspective view, that a square has a less number of multiplication or addition than to find an A inverse, that adjoint of all these things. So that's why computation compute that A square A inverse, that Kalimantan theorem is important. One thing in previous video I missed, that for this field thing, that what is a characteristic polynomial or characteristic root of a matrix over a field? So we have to fix a field. Say if field is R, say your field is R, and if the characteristic polynomial has there is no real roots, all are, say x square plus 1 is a characteristic polynomial, then we cannot say that I and minus I as a eigenvalue. That was a mistake in the previous video. We can't say I and minus I. So if characteristic equation is like that, and our field is R, then we can't say I and minus I is the characteristic eigenvalue or characteristic root. The characteristic root, by definition, that should be in the same field. Now, if there is any general field, the solution of the polynomial may be not in the field. And if there is a concept called algebraic closure, if every field has algebraic closure, that is a theorem in abstract algebra, that every field has algebraic closure. So like complex number is the algebraic closure of real number, that complex field. So there is, for every polynomial where coefficient from f has a root in an algebraic closure, that extended field. Now that if we have a root not in the f, in the algebraic closure outside there, then that number cannot be said as eigenvalue or characteristic. By the way, we talk from the Rao-Vihar-Shankaran that eigenvalue and characteristic roots are two different concepts, but I search in other book, actually the characteristic root and eigenvalue is just synonymous. Characteristic roots, characteristic values, eigenvalues, eigenroots, whatever, these are the same thing. Nothing question of distinct or other thing. So we can't say this as a eigenvalue. So now solution of the characteristic roots is not the characteristic. The solution of the characteristic polynomial is not the characteristic root. The solution of the characteristic polynomial is characteristic root if that root in that for the underlying field. And if this field is itself is algebraically closed field, then there is no problem, because if field is algebraically closed, then every root solution of the polynomial is in that field. But if it's not algebraically closed, there is a problem. Then we can't say that the roots of the algebraic polynomial and the characteristic polynomial is characteristic. We can't say that. Okay, so we just left with one single theorem. We'll discuss on the next lecture this theorem. Let's stop now.